Hello. Today we are going to wrap up Module 3. This was a really long module. The next module is a lot shorter, so you'll get a little bit of a break. But we're going to talk about Lewis structures first, and then we're going to talk about something called polarity within a bond. So we're going to draw structures for different molecules as well as polyatomic ions. And in these structures, we're just considering valence electrons, so those highest energy electrons. And remember, electrons really determine the type of bond that can form between two atoms. But additionally, it's really important to show how those atoms are all bonded to each other within a compound. So off to the right, you can see a table showing some Lewis structures for different compounds. We have CH4, which is methane, NH3, which is ammonia, and H2O, which is water. And we've seen a lot of information about water in chemistry. It's one of the more important chemicals we work with. So we'll learn how to make all of these different Lewis structures. So let's start with a simple molecule. In fact, it's the simplest molecule, hydrogen. So a hydrogen molecule has two hydrogen atoms, and initially those hydrogen atoms might be far apart. And remember, hydrogen is in group 1A. It has one valence electron, similar to the alkali metals in that group. Now, hydrogen itself is a nonmetal, but we include it with the group 1A metals because it has one valence electron. All right, so if these two hydrogen atoms start out far apart, each with their own electron, they're pretty unstable. Remember, atoms want to be like a noble gas. So in this case, hydrogen wants to be similar to helium, which is the next closest noble gas. And helium has two electrons. So what happens is those hydrogen atoms are going to find each other, and they're going to form a covalent bond where they share those two electrons. So now that those two hydrogen atoms are sharing those two electrons, both hydrogen atoms are happy because they are like helium. They're stable. All right, so here's an energy diagram where on the y-axis we have increasing energy, and on the x-axis we have increasing decreasing distance between nuclei. So again, when the hydrogen atoms are really far apart, they don't have any attraction to each other, but they're also really unstable, which means they're very energetic. Now, if those two hydrogen atoms get near each other, they're going to start to attract each other, and eventually they'll get close enough that they share those two electrons and form a covalent bond. So now they're really low in energy because they're stable, like a noble gas. So we can represent a molecule using what's called a Lewis structure. And in this Lewis structure, we're showing the valence electrons of all of the atoms in the compound, and we're showing their arrangement in order to give octets, or 8 electrons, except for hydrogen, which only needs 2. So we can show shared electrons, or what we call bonding pairs, as 2 dots, so kind of similar to what I drew on the last slide. Or we can draw a single line to represent a covalent bond. Now, sometimes you'll have a molecule that has some leftover electrons that are paired. We call those non-bonding pairs or lone pairs of electrons. So in the molecule below, ammonia, which is NH3, There are three covalent bonds between nitrogen and each hydrogen. And then there's this lone pair of electrons hanging out on nitrogen. So we'll talk about how to determine whether electrons are used for bonding or if they're going to be in a lone pair. All right, so again, we're going to draw these Lewis structures to show how atoms share electrons to achieve an octet of electrons. So previously I did show the structure for two fluorine atoms that are bonded together. So again, each fluorine has 7 valence electrons. And when they're by themselves, they're pretty unstable because they have this lone electron that really wants to bond to something, but also fluorine would like to have 8 electrons like a noble gas. So if these two fluorine atoms get close enough, they can form a covalent bond. So they'll form a bonding pair, which is in the middle there. And then there are 3 lone pairs of electrons on each fluorine atom. So we have 1, 2, 3 on the left fluorine and 1, 2, 3 lone pairs on the right fluorine. Now, again, we could also represent that bonding pair as a line, and sometimes that's easier. It just kind of depends on what your preference is. I don't mind if you draw 2 dots or a line, either one is fine. One thing to remember though is that lone pairs are always represented by 2 dots. We never show lone pairs as a line. That's only for bonding pairs or covalent bonds. All right, so then we have our fluorine molecule. Now, you might have noticed throughout this quarter that there are some molecules where, or some elements that are always found in a pair, like oxygen. And now we can see fluorine and hydrogen are also found in pairs. So these are what we call diatomic molecules. So there are certain elements that are just always found in a pair with themselves. So that's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those all exist as diatomic molecules. So on the periodic table, it looks like an upside down L plus hydrogen. So that's one way to remember which of the elements form diatomic molecules. The other way that I've seen a lot of students remember this is the acronym Hofbrinkel. So this is kind of a made-up acronym here, but we've got hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So Hofbrinkel. So if you can remember that, you can remember the diatomic molecules. And this will be important later when we start writing out some chemical reactions, because, for instance, let's say that a reaction produces hydrogen gas. Hydrogen doesn't exist on its own as a single atom. It actually exists as a diatomic molecule. So that's going to affect how we write chemical reactions. So that is important to remember. Okay. So anyway, back to Lewis structures. The number of electrons that a nonmetal atom shares and the number of covalent bonds that it forms is usually equal to the number of electrons it needs to achieve a stable electron configuration. But there are a couple of exceptions. So for instance, hydrogen will form 1 bond because it has 1 valence electron. And that does not follow the typical rule where an atom wants 8 electrons, right? So again, hydrogen only needs 2 electrons to be happy. Boron is another exception, so it has a little asterisk next to it. Boron, remember, is in group 3A, so it has 3 valence electrons. So it can form 3 bonds because it has 3 unpaired electrons. Now, if it does pair up with other atoms, so let's say boron pairs up with 3 hydrogens. Boron only has 6 electrons there, so 1, 2, 3, 4, 5, 6. But boron is totally happy with just 6 electrons, so it's another exception to our typical rule. Okay, so now everything else will follow the rules. So if we look at carbon, carbon is in group 4A and it has 4 unpaired valence electrons. So it can form 4 bonds. And same with silicon just below it. In group 5A, we have nitrogen. And nitrogen has 5 valence electrons, so that's 1, 2, 3, 4, 5. So nitrogen does have a lone pair of electrons, and it has 3 unpaired electrons, so it can make 3 bonds. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. So it has 2 lone pairs and 2 unpaired electrons. So those 2 unpaired electrons really want to team up with other electrons so that oxygen will have 8 total electrons. So that means that oxygen can make 2 bonds. And then we saw with fluorine, it has 7 valence electrons. And it has only 1 unpaired electron, so it can make only 1 bond. All right. Okay, so let's practice drawing a Lewis structure for phosphorus trichloride. Now, there's a couple of different ways that you can figure out the Lewis structure, so I'll show you both ways to do it. So in the first method, what you can do is draw the Lewis symbols for both atoms that are present in this molecule. So for instance, phosphorus, if we go back, phosphorus is in group 5A. So it has 5 valence electrons, similar to nitrogen. And then chlorine, if we go back, is in group 7A, so it has 7 valence electrons. I'm going to put its unpaired electron off to the side there. Okay, now there are actually 3 chlorine atoms, so what we could do is try to pair up any unpaired electrons. So maybe we start drawing those chlorine atoms kind of surrounding the phosphorus atom. Okay, so now we can kind of see where we might start to form some bonds here. So phosphorus has 3 unpaired electrons, which could team up with the unpaired electron on chlorine. And conveniently, we have 3 chlorines. So each unpaired electron on phosphorus can team up with a chlorine atom. Okay, so we could also draw this with lines representing those bonds. But remember, the lone pairs are going to stay as dots. All right, so that's one way to try to figure out a Lewis structure, but sometimes it takes some guesswork. Instead, let me show you another way that has some rules that we need to follow. And this will help you with more complex structures as well. Okay, so I'm going to erase this, and I'll show you how to figure out the Lewis structure with some rules. Okay, so first what we're going to do is count valence electrons. And we want the total number. So phosphorus again has 5 valence electrons, and then we have 3 chlorines that each have 7 valence electrons. Okay, so 7 plus 7 plus 7, or 7 times 3, that is 21, plus 5 is 26 valence electrons. Okay. So now 2, we're going to figure out which atom goes in the middle. So typically the atom that goes in the middle is by itself or forms the most bonds. So the central atom is either by itself or forms the most bonds. Okay, so we already saw that phosphorus has 5 valence electrons and it can form 3 bonds. Chlorine has 7 valence electrons and can only form 1 bond because it only has 1 unpaired electron. So that means phosphorus must go in the middle. So next, we're going to form the molecule skeleton. So we're going to put phosphorus in the middle, surrounded by chlorine atoms. So it'll look something like that. Okay, so I'm going to erase this and then continue. So if you're taking notes, you might want to pause the video and just write this down before we move on. Oh, actually, I'm just going to clear the pen markings. There we go. That's much faster. Okay, so now we have our basic structure. And the next step, number 4, is to place bonds between atoms. Okay, so I'm going to put a bond between each of the chlorines and phosphorus. Now remember, each of those bonds represents 2 electrons. So far I've used 6 electrons. So originally we had 26 total electrons, and now I've used 6, so I have 20 electrons left. So in step 5, we're going to place the remaining electrons around outside atoms first, and then if we have any leftover electrons, they'll go on the central atom. So here, I'll use a different color for these electrons. Now, when we're placing remaining electrons around the outside atoms, we're trying to give each atom an octet. So let's focus on the chlorine on the left. It already has 2 electrons that it's sharing with phosphorus. So now we want to give it 1, 2, 3, 4, 5, 6 more electrons, so it has an octet. So that's 8 electrons total. Let's do the same with the other 2 chlorines. Okay, so now let's see, let's count how many we've used up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons that we've used. So that means we have 2 electrons left. So those are going to go on phosphorus. So remember, we're trying to give each atom 8 electrons. So make sure each atom has an octet. All right, so let's highlight what phosphorus has. So phosphorus has ownership over, oh, I did not mean to do that. Let's see. Oh no. Let me fix my mistake here. I meant to highlight it. There we go. So phosphorus has ownership over the electrons on the top, off to the left, off to the right, and down below. Now it has co-ownership over some of those electrons. So it has a total of 2, 4, 6, 8 electrons. Perfect. Now what about each chlorine? So each chlorine has ownership over its shared electrons with phosphorus, and then its 3 lone pairs, which is 8. And each chlorine looks pretty similar. So everyone has 8 valence electrons. Everyone is happy. Perfect. So again, you can try to figure out Lewis structures just by drawing the Lewis symbols and kind of piecing things together. Or you can follow these 6 rules or 6 steps that we went through. Either way is fine as long as you get the right answer. So whichever way works best for you. All right, and here's some solution slides to kind of help you step through that as well. Now, sometimes we need a double or a triple bond in order to make a molecule work or give each atom 8 valence electrons. So as an example, we have CO2 off to the side, and this has 2 double bonds. And those double bonds represent 4 shared electrons each. So the double bond on the left is worth 4 electrons, and the double bond on the right is worth 4 electrons. So carbon has a total of 8 electrons. And in a triple bond, you're sharing 6 electrons. So for instance, in this HCN molecule, or hydrocyanic acid, we have 6 electrons in that triple bond, and 2 electrons in the single bond. So that's a total of 8 electrons that carbon has. So we're going to look at a couple of examples just to get a feel for how and when to form double and triple bonds. Now there are some exceptions to the octet rule, so before we get started on that. So again, hydrogen requires only 2 electrons to be happy because it's trying to be like helium. There are also some nonmetals like phosphorus, sulfur, chlorine, bromine, and iodine that can form what's called an expanded octet. So sulfur, for instance, does form compounds like this one over here, where it's bonded to 6 fluorines. And if we count each of those electrons, we have 2, 4, 6, 8, 10, 12 electrons that sulfur has co-ownership of. So that's way more than 8. But this is a fairly stable compound, so it does occur naturally. Phosphorus can form compounds with 10 electrons. So there are exceptions to the octet rule. Also, we talked about boron. Boron's happy with just 2, 4, 6 electrons. So it only needs 3 bonds there. So even though we typically try to give every atom 8 electrons, there are some situations where an atom might have more or less. So just something to keep in mind. Okay, so let's practice drawing some Lewis structures. So let's draw the Lewis structure for SO3, which is sulfur trioxide, and CO, which is carbon monoxide. All right, so let's start with SO3, and we'll go over this together. So again, the first thing we're going to do is count up the number of valence electrons for the molecule. So sulfur and oxygen both have 6 valence electrons. So we have 6 electrons for sulfur, and then 6 times 3 electrons for each of the oxygens. So 6 plus 6 plus 6 plus 6. So sulfur, oxygen, oxygen, oxygen. Okay, so that's 6 times 4, which is 24 total electrons for this molecule. All right, so the next step, we have to figure out which atom goes in the middle. So remember, that's either the atom that is by itself or the atom that can make the most bonds. So sulfur, again, has 6 valence electrons, and oxygen has 6 valence electrons. Okay, so it looks like each of them can make 2 bonds. So in this case, sulfur will go in the middle because it's by itself. So I'm just going to draw sulfur in the middle surrounded by oxygen atoms. All right, so now the next step, we're going to make some covalent bonds between sulfur and each of the oxygen atoms. So that means we've used up 2, 4, 6 electrons out of our total of 24. Okay, so 24 minus the 6 that we used is 18. Okay, so we've got 18 electrons left. So let's place those electrons around the outer atoms first and give each of those outer atoms an octet. All right, so I'll start with the oxygen on the left. I'm giving it 8 electrons here. And I'll do that for each of the oxygen atoms. Okay, so it looks like we've used 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. Okay. So now let's go through and make sure everything has an octet. So I know each of the oxygens has an octet because I made sure that they did. So this oxygen is happy, that oxygen's happy, this oxygen's happy. What about sulfur? Does sulfur have 8 electrons? No, sulfur only has 6 electrons, so it is not happy. Okay, so this is where we might need a double bond or a triple bond in order to make sure everything has 8 electrons. All right, so what we're going to do, I'm just going to move some electrons around. So I'm just going to arbitrarily move a lone pair of electrons from the oxygen on the right over, and I'm going to make a double bond. Oh, actually, let me be consistent. I'll put those electrons on the bottom. Okay, so now let's just double check that the sulfur and the oxygen on the right still have 8 electrons here. Okay, so sulfur has 2, 4, 6, 8 electrons. Great. And oxygen has 2, 4, 6, 8 electrons. Awesome. So it's totally valid to move lone pairs of electrons around to make double or triple bonds in order to make sure that each atom has 8 valence electrons. So that is our final structure for SO3. We have 2 single bonds and a double bond. All right, so now let's look at carbon monoxide. Okay, so B. Let's count up how many valence electrons we have total. Carbon has 4, oxygen has 6. So 4 plus 6, this is carbon, oxygen. So that gives me 10 electrons to work with. Now for this structure, we only have 2 atoms, so they'll just be side by side. We don't really have to figure out which one's in the middle. And I'm going to draw a bond between them. So I've used up 2 electrons. So that's 8 electrons left. So let's see. I think I'm going to divide the electrons equally between them. So I'm going to put 4 electrons on carbon, and I'll put the other 4 on oxygen. Because typically molecules like to be symmetrical anyway, so I'll just start there. All right, so let's count up how many electrons each atom has. So carbon has 2, 4, 6. Ugh, okay. So carbon is not happy. Oxygen has 2, 4, 6. Okay, so neither atom is happy. So maybe what we'll do is move one of these lone pairs over so that they're sharing some electrons, some more electrons. So that would look like this. Okay, so now let's count. So carbon has 2, 4, 6 still. Ugh, okay. What about oxygen? Oxygen has 2, 4, 6, 8. Okay, oxygen's happy. So maybe what we'll do is move some electrons from oxygen over, and then it'll share more electrons with carbon, and hopefully carbon will have 8 electrons. Oh, okay, so let's move this pair over. So we're going to form a triple bond. All right. Okay, so let's count electrons. We've got 2, 4, 6, 8 for carbon. Yay! And oxygen has 2, 4, 6, 8. Okay, perfect. So this is the Lewis structure for carbon monoxide. There's a triple bond between carbon and oxygen, and each atom has a lone pair of electrons. So again, feel free to move pairs of electrons around in order to make sure everything has 8 valence electrons. Unless, of course, you have hydrogen or boron, and then they're the exceptions. All right, and here's the solution slide. So actually, I think I'm going to end the video there and do a separate video on electronegativity and bond polarity, because this was already kind of a lengthy video. So we'll just do one more video for module 6, or module 3, excuse me, and then we'll move on to the next module. So I'll see you then.